All right, so I'm going to talk about the practical op-amp model first, and then I'm going to move over to the ideal op-amp model because the ideal op-amp model is what we're actually going to use when we solve circuits. And so let me just make this distinction one more time. What do I mean when I say practical versus ideal? So ideally, we want the op-amp to behave a certain way, but in real life, there are practical limitations. And so in real life, when we practically implement an op-amp circuit, we have some practical limitations is all really, and one of those things is called the input resistance, the finite input resistance, right? That's this value here of Ri. And what I mean when I say that this input resistance is finite, let me first talk about what would happen if this resistance were infinite, right? If this resistance were infinite, then I would not be able to get any current flowing through this resistor, right? There would be no current flowing. The impedance or the resistance would be way too large. It's infinite. And what that means is there could be no voltage drop across this resistor. They have it drawn from plus to minus like this because I think a lot of people, basically moving forward, we're probably going to see, instead of seeing the plus terminal here and the minus terminal here, we're going to see it flipped. The reason for that is because of the way that the op-amp topologies work. It has nothing to do with the operation of the circuit. It's really just for the convenience of drawing. But let me get back to my point. So this is my plus terminal, this is my minus terminal. If this Ri is infinite, then that means no current can flow through this. If there's no current that can flow, then that means that Vd has to be equal to 0, right? And if there is no voltage drop across this resistance Ri, then these two voltages have to be equal. And that's what I said in the previous slide, right? That for an ideal op-amp, these two voltages are equal to each other, right? Well, for a practical op-amp, that's not the case. The Ri might be very, very, very large. And so these voltages will be close to equal, but they won't be exactly equal. So that's one limitation of the practical op-amp, is that there is a finite input resistance value, which means that these two values will not be exactly equal to one another. Okay? The second practical limitation of the op-amp model is the open loop gain, or A. I guess in the previous slide I called it AOL, which is just basically the gain, and then I use a little subscript OL to indicate that we're talking about open loop. And what the heck do I mean by open loop? It doesn't really matter right now, but we typically operate op-amps in feedback, which means we're going to connect one of our inputs actually over to the output side, namely our minus input. And we do that for a number of reasons. I'll talk about that in a couple of slides. But like I said, the open loop gain, we want to ideally be as large as possible. Why do we want it to be as large as possible? Well, if I go back to this slide, the larger this is, the smaller this difference can be in order to give me the output voltage that I want, right? And in order to solve op-amp circuits and to make their behavior predictable, I need this open loop gain to be very large because I want this Vp minus Vm to be very, very small. I want that difference to be close to 0 so that I can easily solve the circuit, right? And so another practical limitation of the practical op-amp is finite open loop gain. It's not infinite. This value of A is not infinite, right? Okay, and then the last thing is non-zero output resistance, okay? And so let's look at this circuit right here, and let's just pretend there's no triangle there, and let's just look what we have. Well, we have a voltage source, a dependent voltage source, which is the open loop gain multiplied by the voltage drop Vd across that resistor, which is exactly what I had in this slide, right? It's the open loop gain multiplied by the voltage difference across the input. That's exactly what this dependent source is saying. Well, let's say that I want to, drive some kind of a current through some resistor on my output. If I have a output resistance R0 here, now I'm left with the voltage divider, right? Where some voltage is going to have to be dropped across RO before I can get anything at V out, okay? Where in an ideal op-amp, this is just a wire and no voltage is dropped at the output. In a practical op-amp, there is a non-zero output resistance. And so we lose some of the output voltage across our non-zero output resistance, okay? So this is all pretty complicated stuff, probably not stuff that we really care to think much about But I want to make sure that it's at least been covered in case you have any questions and don't understand how op amps work. This is really the getting deep into understanding why the op amp works the way that it does, and what the practical limitations are. It's pretty important in order to really understand what's happening in op amp circuits. Might not be important for solving them. All that I think is really important for solving them is the two golden rules. But in order to understand why the golden rules are what they are, it's important to look at practical op amps and ideal op amps. And so let's look at the ideal op amp. Well, the ideal op amp is the one that we're going to be using when we solve circuits. And like I said, the first key point is that it's got infinite input resistance. So this RI value is infinite. If that's infinite, then that means that my V1 and V2 are at the same potential, right? Because no current can flow through this resistor, so the voltage drop VD goes to 0, right? So that's the first thing. The second thing is that the open loop gain is infinite, right? Which I talked about in the first slide. The open loop gain is infinite. And the last thing is that the output resistance is 0, right? So this resistance here is just a short. There's no resistance there, so we lose no voltage across that output resistance, and all the voltage becomes, it shows up at our output. So if we wanted to drive a current or some kind of a load through some kind of resistor, then all the voltage would show up across my resistor, and I would have no voltage drop or droop at the output. Okay, so we talked about the practical op amp and the ideal op amp. In the next video, I'm going to talk about feedback, which is kind of the last little preliminary topic before we actually start solving some circuits. This is all really just an overview of op amps, how they work, why they work the way they do. And in the next video, I'm going to go ahead and talk about feedback.